Popular science fiction has included space for a very long time. With today's CGI and filmmaking technology, space movies provide us with the thrill of exploring the unknown and are also pretty spectacular to see. However, we're not arguing that movies have to be perfect. After all, to appreciate fiction, some degree of suspension of disbelief is necessary. All we're suggesting is that if screenwriters checked up a few things online before writing their drafts, our conception of space could be a little bit more accurate. 10 space myths we assume due to films. Without a shot, one of the top 10 things in life is seeing a massive space explosion on a large high-definition screen. Putting aside the striking images, whether or not those explosions can actually occur scientifically is a very different question. Because of air and gravity, explosions on Earth, from which the movies draw their inspiration, seem as they do. The explosion is caused by the air acting as an oxidizer, which causes it to fly outward before collapsing back into the Earth due to the blast's external pressure. But explosions in space would differ greatly from that. Even without air, there would still be some fire since some fuels may work as oxidizers, albeit it wouldn't look like fire as we know it. As a result of the microgravity and absence of air resistance, this fire would appear to be a ball of light that is constantly expanding. The surrounding spacecraft would also be at risk since the shrapnel would keep spreading until something stopped it. In movies, black holes are represented as all-consuming vortex of devastation and despair that are impossible to escape from if you're nearby. While the majority of us have no more information to rely on because the physics books are too difficult to go through, that is how we generally perceive things. Yet if you read even the most elementary academic explanation of black holes, you'd see that we've misread them terribly. They are identical to every other celestial body in the cosmos since their pull is inversely correlated with their mass. They can only draw as much as their size will allow. Nothing in the solar system would change, at least gravitationally, if our sun were somehow replaced by a black hole as enormous as it. This is because the sun is quite significant in other domains. While it is true that a black hole will devour everything that is close to its event horizon, everything outside of that area would only be subject to the regular gravitational effects of the black hole. The asteroid belt is a region that divides the solar system's inner and outer planets. Movies have always made a point to employ this ring of asteroids and other debris that revolves around the sun, as the name makes obvious. They typically depict the belt as a congested place with dense clouds of pebbles that you must masterfully navigate through to reach the other side. We regret to inform you that your mental picture of the asteroid belt is wildly wrong if that is how you have always believed it to be. Because of the distances involved, the sky from an asteroid in the belt would resemble the sky from Earth quite a bit. There is extremely little possibility of a collision for any spacecraft passing through it since the asteroids are widely separated and far from one another. Because it is the only frame of reference we have, it makes sense that we would model space combat after conflicts on Earth. Space battles resemble the dogfights we see in World War II movies, with a spaceship engaged in combat similar to that of an aircraft on Earth. These wars may appear amazing, but they are not grounded in fact. Actual space combat would likely not resemble what is seen in films, with battle vessels made with radiation resistance and decompression prevention in mind rather than aerodynamics. Also, traditional dogfighting strategies wouldn't be effective in space. The movement and maneuvering in a genuine space combat would be foreign to someone who grew up watching Star Wars, even if the general battlefield tactics of Earth-based conflict would still apply and envelopment would probably still operate the same way. Most of us still don't understand how the sun truly functions, despite the fact that it is the primary cause of life on Earth. Because we presume that it is burning and that is how fire appears, we may believe that it is yellow in hue. That also implies that we don't really know why the sun produces so much heat. For starters, the sun is not at all yellow and only seems that way because of the Earth's atmosphere. Pure white is the color of sunlight. What's more, the sun isn't really burning, at least not in the sense we often think of the word. The sun's heat is produced by fusion reactions between numerous molecules in its core rather than an eternal fire. We visualize the numerous solar systems around the cosmos as being identical to our own. Depending on whether the system contains planets, there is a fixed star in the center, with a variety of celestial bodies around it in ellipses or circles of varying diameters. Because gravity is a two-way force, both the Earth and the Sun are tugging on us. The Earth's gravitational pull on the Sun is so little that we simply don't sense it. However, this is not true for larger planets. When it comes to Jupiter and the Sun, they really revolve around a location in space outside of the Sun's atmosphere. This impact would be significantly stronger in systems with several massive planets, such as Jupiter. We don't often see every solar system in the cosmos in that way. For a long time, sci-fi movies have included laser weaponry. Most people would be dismayed to learn that they don't resemble the movies now that we're so close to witnessing them in action on the battlefield. A laser beam, which has been overused by space opera directors, is essentially a focused burst of energy that may be utilized for a variety of purposes on the battlefield. Nevertheless, unlike in the movies, there shouldn't be any particles in space to scatter the light, thus real-life laser beams would be absolutely undetectable. Since there is no gravity in space, it makes sense that it is commonly thought that you are weightless. It is supported by a large number of fiction and film productions, and there are several videos of humans appearing to be weightless in space. Although many astronauts do experience a sense of weightlessness in space, this only occurs when you are in an orbit around a larger body. For instance, it occurs on the International Space Station. Other than that, no matter how subtly, you are always subject to the pull of gravity. Unless you're in a constant fall around a planet or other celestial body, like the ISS is, you're never completely weightless in space. While gravity exists everywhere in space, we're not sure why movies continue to depict it as such. The space movies of the last century are primarily responsible for the notion that you can hear the noises of explosions in space. It's not true. Without air and with molecules vibrating, sound simply cannot travel through space. We need to be grateful for this as well, for if it weren't for it, we could always hear the noises of the cosmos, such as the continuous thermonuclear explosion that is our Sun. Even though we can now more accurately simulate real-world physics, we still utilize the cliché of objects bursting in space and producing loud noises because it looks better on screen than merely a silent image. Although certain films, such as Stanley Kubrick's 2001, A Space Odyssey, have been able to get this one right, they are more the exception than the rule. As it is typically believed to be unsurmountable, the speed of light is regarded as the greatest obstacle facing humanity. There are many speculations about what it will be like to get there, but none of our calculations take anything beyond that into consideration. The universe's rate of expansion is the only known phenomenon in it that moves more quickly than the speed of light. Though we don't fully comprehend it, it has been discovered that the universe is expanding faster than the speed of light. This discovery has baffled scientists and amateur astronomers alike. The pace of its growth increases in direct proportion to the distance from us. The more distant anything is from us, the quicker it is departing. That's not all. Although we haven't yet been able to locate them in nature, there is scientific evidence, albeit speculative, of particles that may move faster than the speed of light. The only thing left to do is identify the other objects that could break the light barrier, according to several experts. Don't forget to like our video or subscribe to our channel. See you in the new video. Goodbye.